A monad is a container that holds a value and provides methods to transform or chain operations while managing context. Context could mean things like null checks, error handling, or async operations. Monads can simplify operations by extracting common patterns like checking for null into reusable structures. And that's exactly what we're going to do today. But first, we're going to take a look at some monads you might already be familiar with, including Nullable. Let's get started. A monad is a design pattern that represents computations or values within a context, providing a way to wrap values, chain operations while preserving the context, and inject values into the context. Most of you have already been using monads in your coding. For example, a task of type T is a monad because it wraps a value in an async context, and it allows chaining operations with continue with or await, and it ensures the asynchronous context is preserved. Enumerable of type T is a monad because it represents a sequence of values, it supports chaining transforms using select many, and it maintains the sequence structure. A nullable of type T is also a monad because it wraps a value in a context that represents the possibility of null. It still allows transforms with select, and it ensures the absent state is preserved through operations. Most programmers don't explicitly write nullable, instead they use the nullable operator. So just as a trivial example, if we defined a list of integers here where some values in the list are null, you can see we have compiler errors right away. However, if we were to change this to a list of nullable ints, then it's fine, no problem. But that does mean you're going to have to anticipate that some values in this list will be null when you're trying to process the items. Let's make a non-trivial example. Suppose in this async processor class, we have a method processItemsAsync where we accept a list of enumerable of type nullable t. So here we can await the task to run, but we're going to filter out the null values and only apply the processor function that we passed in to the ones that exist. This is taking advantage of the fact that the nullable has a hasValue property and it also has a value property. Let's collapse up this class and take a closer look at this in the example. Here, I'm just going to wipe out this list. We don't need this anymore. But let's create a start method. Inside of start, I'll declare a nullable score. Now, instead of having to do a null check on this value, we can instead just do something as simple as this. If it has a value, we do one thing. If it doesn't, we do something else. This gives us a clear, type-safe way to represent the possibility of no value and reduces the risk of a null reference exception. It makes the intent explicit without requiring manual null checks. Now, let's move on to talk about the default keyword for a moment. So default initializes a variable to its default value. So for value types like int, that's going to be 0. For reference types, it will be null. Now, some of you in your coding journeys may have encountered this expression. The exclamation used after the default keyword here is the null-forgiving operator. This suppresses compiler warnings for uninitialized nullable reference types. The default in Unity is that nullable reference types are disabled. That means that all reference types behave as if they could be null, and the compiler does not generate any warnings about potential null dereferences. So if you were to do something like this, of course, you're going to get a null reference exception. Now, there's two main reasons this is disabled by default in Unity. The first one is backwards compatibility. This is a C#8 feature. And of course, there are always issues with Unity engine.object, which has an overloaded equality operator and handles nulls in a special way. But how about just for interest's sake, we turn this on for a moment in Unity. If I navigate over to project settings in the player section, down at the bottom, there's additional compiler arguments. I'll add one more here to allow nullable reference types. When I click apply, it's going to start recompiling the entire project, and I'm going to speed this up a lot because it's not just going to recompile my code, but all code. As it finishes compiling, we can see over 6,000 warnings here. This means the compiler is now tracking nullability and it's detecting potential issues in the code where reference types may be unintentionally null. Potentially, these are all areas that need review for null safety. I'm going to disable this again. That was just for an example. We don't need to be overwhelmed with thousands of warnings. Before we dive into monads, let's have a look at the null object programming pattern. If I declare an interface here for an iAudio player that just has one method, we could create a concrete version of this that would actually play something. Beyond that, we can also declare an iAudio player that actually does nothing. That's really what the null object programming pattern is. It creates objects that do nothing. So for example, maybe I have a list of players, each player having an iAudio player, but some of those players have disconnected, or for whatever reason, the entry in this list is null. Now I might be passing this list into some sort of processor that plays all the sound. If some of these entries are null, you can see right away there's going to be an issue. The null object programming pattern solves this issue. Instead of having nulls in your list, you have a null object. That way, when you iterate over all of them, you won't get any null reference exceptions. Instead, they just do nothing. So we're not going to dwell on the null object programming pattern. It has its uses. Instead, I want to take a look at handling nulls a different way, and that's with a monad. .NET has an optional monad, but it's not available to us in Unity. So we're going to create our own. Now, before we actually write the code for an optional monad, why don't we see what it can do for us? Let's suppose that we're building an inventory system and we have a bunch of items. Each item, for now, will just have a name. Items are going to go into inventory slots, but each slot is optional. It doesn't need to have an item, so we're going to default it to an optional of type item.none. This is very similar to the null programming pattern, where here none is going to represent an optional item with no value. Let's create a helper method here, add item. We'll take in an item, and there we'll use the sum factory method to create a new optional item. This is just going to wrap the item into an optional. Now, there are many ways to use an optional. Let's have a new method here, use item. One way is to use the match method, which expects two delegates. One is when there is a value, and one is when there isn't a value. Now, another way to do this, similar to what you'd do with a nullable, is you would say, if the item has a value, then we do one thing, otherwise we do something else. Now, if we were to go back to the other version, another way you could do this is actually pass in delegates that you would pass into the match method. This would make it quite a bit more dynamic, but the match method, the way it's written right now, is meant to return values of the same type. So here we could run the action and just return 0 in both cases. Alternatively, you could return default, or you could just use funcs that already have a return type. Just make sure they're the same. This is because match is often used in chaining. And speaking of chaining, why don't we look at how we can compose this a little bit more? What if we had another optional int called durability? Then maybe we want to create some kind of string description of this inventory slot, or just do some debugging. Here we can combine the two optional values, item and durability, to produce a summary or a fallback message if either one is missing. So select many will chain item and durability. If both exist, it will create a string. If either is missing, the chain stops and skips the combination. Match handles the result. If the summary exists, return it. Otherwise, return item or durability missing. So this safely combines optional values with some fallback logic. So that's just a small peek at the power of what you can do with these kinds of monads. Why don't we actually write the optional class? Let's start by defining a generic struct for optional values. Let's have a static instance of this that we'll call no value. This will just represent the absence of value. Then let's add a bool that will track if the optional has a value or not. And let's have a type t that will hold the value if it's present. Then let's create a constructor that'll take in a value t, set it, and set the has value to be true. We can make our sum factory method so that we can create an optional with a value. And likewise, we're going to have its counterpart, which is none, and that will just return no value. Let's also handle equality. First of all, let's override equals, but let's also create a strongly typed equality method. This will avoid runtime type checking when we know both objects are optional. On top of that, of course, we need a get hashcode method, and we might as well implement a toString while we're at it. Now below this, we can have an implicit conversion from t to optional of type t. We could also have an implicit conversion from optional type t to a bool if we wanted. Then we'll have an explicit conversion to retrieve the value. Of course, we haven't defined a value property yet. Let's come back up here to the top. So we'll have a public value property. It'll throw an exception if there's nothing there. Let's also have a public property for the has value. Then let's have a few more helpers. Let's have one that returns the value of present, otherwise returns the default value for t. We could have another one where we pass in a default value for t. So now we can start looking at some of these more specific methods. For match, we can take in two funcs, and based on has value, we'll either process the first one or the second one. Notice that only the first one accepts the value to process on. We could have a select many. This could chain another optional producing function and flatten the result. And we can have a normal select function that will just do a transform on the value. We should always check has value before starting to do one thing or the other thing. And then finally, let's have a combine method that will take in two optionals and a func that will do the combining. So it'll check to see if they both have a value. It'll run the combiner func and return the result. Otherwise, returns no value. And that, in a nutshell, is a very lightweight version of an optional monad. Now, of course, you could add many more overloads. You could have your selects, your match methods take in actions instead of funcs if you don't want return types. There's all kinds of things you could add to this to make it more robust. You could look up optionals in the .NET library if you want some ideas for more additions you could put in here. But anyway, let's move on. So the other kind of monad I want to talk about today is either. Either is a lot like optional, except here we're expecting one or the other. You might want to return something different when the quest is successful than when it fails. So in this example, suppose we're completing the quest and we pass in a Boolean to represent success. We can say if we're successful, we're going to return either where the right side of the value is 100. So maybe we've earned 100 gold or 100 points. If we fail, we'll pass back a string that just says quest failed. Now, traditionally in functional programming languages, the left side represents errors or failures, while the right side represents successful computations. So you can remember that by thinking like right is right. So let's put this to work back up in our example class. Let's make a new method here, handle quest result, that'll take in an either result. Now, maybe the player is on some kind of bonus scheme. We could use the select on this either to actually give them a little bonus, maybe 50 more gold. Then maybe we could use the match method to actually produce some kind of message for them. Just for now, for our testing, let's debug that to the console. And you know what? Why don't we just inline this whole thing? And if we come up to the start method, let's create a new quest and we can test out our method by passing in true or false. Now, just like the optional monad, you're going to be able to use either to chain into all kinds of other methods. So why don't we go and write the either class right now so we can explore the possibilities a little bit. I'll go through this pretty quickly because it's really not that much different than an optional. Firstly, we need variables to hold the left value and the right value, and maybe one to indicate if it's the right one or not. For an either, I'm going to keep the constructor private because I want to use static factory methods to create them. The constructor will take in the left, the right, and the Boolean for isRight. We can add some helper properties to tell if it's the left one or the right one. Then let's add some public properties to actually get these values. We can return the left one as long as it's not the right one. If we're supposed to be using the right one, let's throw an exception. If it is supposed to be the left, we'll return it. Let's do exactly the inverse for the right. Now, those take up a fair amount of real estate. I'm just going to collapse them up and then let's continue. Let's make some factory methods to create a left. Let's have a factory method that will create a right. Then why don't we implement some of these specialty methods like match? So for match, we're going to match the value to one of the two provided functions. So we can say if it's the right, we're going to run the right func on the right value. And if it's the left, we'll run the left func on the left value. Then we can have a select that'll do a transform on the right value using a provided function. So if it's right, we'll run this map function on the right value. Otherwise, we'll just return a left. We can have a select many. Here we can chain another either producing function and flatten the result. Again, if it's not a right, we're going to return a new left. Now let's finish this up with a few little helpers. Let's have a toString method. Let's also get some implicit operators so that we can easily convert from a T left or a T right to an either. Now, why don't we go make sure that this works the way we think it does? Well, there's not too much to demo today because it was mostly code, but let's have a look in the debug log here. So ignore the first line there. That's for next week's video, but you can see right under that, success earned the 100 gold plus the 50 bonus. And if we passed in a failure, of course, we see our failure message. So these two monads that we built today can be expanded on quite a lot. The .NET implementation of an optional is very robust. And if you want to see other implementations of either, it's worth looking at the one of library, which is similar to either. It's just called one of, with the idea being that it's one of many things, not just two. So let me know in the comments below how you handle nulls in your games. Are you just doing null checks for everything? Or maybe you have a different way of handling things that I haven't even covered in this video. Maybe we can even include some monads in the Unity utility library. So that's all I've got for you today. Maybe some of you can guess from the screen here what next week's video is going to be about. In the meantime, maybe I'll see you on Discord. Don't forget to like and subscribe. I'll throw another video up on the screen about some more intermediate advanced Unity C#. Maybe I'll see you there.